So this is lecture 4. 4 days in summer is like 4 weeks or 1 month in the semester. And what we've done in the first 3 lectures is develop some elementary number theory that is essential in cryptography. And so let's begin to talk a little bit about cryptography today. And classically, one thinks of 2 people, Alice and Bob, and one wants to send a message to the other. So we have Bob and we have Alice, and Bob wants to send a message to Alice, but there is an enemy who wants to intercept and understand and get the message, and that's Eve. And Eve is looking at the transmission line from Bob to Alice. And just to be safe, we have to assume that everything Bob sends to Alice, Eve can intercept and read. So if there's a message M that Bob wants to send to Alice, but that Eve does not obtain, then Bob obviously has to encrypt the message M. So there is some encryption function, E, and you plug in this message M, and you will get out some encrypted message C. So M is what is called the plain text of the message. It's just the message. We attack at dawn. We'll invade the Germans on the beaches of Normandy. We don't want them to know it's Normandy, though. So you have to tell the soldiers where to go. So when it's encrypted, the encrypted message is called the ciphertext. And the process of going from M to C, the plain text to the ciphertext, E, is called encryption. And the process of taking the ciphertext and getting back the plain text M is called decryption. Right? So every subject has its words, and here are 4 of them: plain text, ciphertext, encryption, decryption. And usually, in order to encrypt a message, you have some encryption algorithm, but it requires some key. So for example, if we have a simple substitution cipher, we're going to replace every letter in the message by the letter that comes K steps afterwards in the alphabet. When you write the alphabet in a circle, the encryption is some key, K. So you require, encryption requires some key, call it K. And if you have what is called a symmetric code, a symmetric cipher, you need the same letter key, K, or the same key, K, to decrypt your message. So decryption also requires the same key, K, whatever it might be. So in a symmetric cipher, Alice and Bob have the same information, and that information is the key K that you need to encrypt and decrypt. So if you want to express this in a kind of a mathematical way, you have some set script K, which is the set of keys. You have the set M of plain text keys K. These are the plain text messages, M. And you have a set C of ciphertext messages. So encryption is a function. So given a key and a message. So this is a set of all ordered pairs, K and M, where K is in the set script K of keys, M is in the set script K of messages. So given a key and a message, encryption gives you some element of the ciphertext C. So every pair KM gets sent to some C. And decryption is a function D, where for every set K, every key K, and ciphertext C, so for every pair KC, when you apply the function D to this, you get back a plain text message M. So K comma C goes to M. So this is your encryption scheme, and this is your decryption scheme, written in a kind of mathematical way. And it has to satisfy two properties. First of all, of course, if you start with a key M, a key K, and a message M, and you encrypt it, you get a ciphertext. And then if you take the key applied and the ciphertext and you apply decryption, you get back M. So this is in some sense the mathematical formula that describes a symmetric cipher. Right? You have a key K, you encrypt your message M, you get this message E of KM, that's a cipher. You decrypt it by applying, you have decryption function that K comma this gives you back M. So M goes to C, comes back to M. That's what's going on. And but it's very critical that the function E of KM must be one-to-one. Because the worst thing that can happen is, suppose M is different from M prime, but E of KM equals E of KM prime. So when you encode M and you encode M prime, you get the same ciphertext. So then if you apply decryption to K and C, that's decryption of K and E of KM, which is the same of E of KM prime. What do you get? M or M prime. You cannot decrypt. The same ciphertext could have come from two different plain text messages if your encryption algorithm is not one-to-one. So one of the criteria for a good encryption scheme is that it be one-to-one. Given the key and a message M, you get a unique cipher C. You don't have two different messages, two different plain texts that produce the same ciphertext. Okay. So this is one thing we always want to keep in mind when we're analyzing an encryption scheme. So if we want to think about cryptography, what are, let's say, characteristics or properties of a successful cipher? Cipher just means an encryption scheme. So here are some properties we would like. For every key K in the set of keys and plain text M in the set of possible messages, it is easy to compute E of Km, which we sometimes write as E sub K of M. That is, if you know the message and you know the key, it's computationally easy to encrypt the message. And similarly, for every key and every ciphertext, C it is easy to compute D of Km, or sometimes we write D sub K of M. That is to decrypt. So it should be easy to do the calculations. The encryption process and the decryption process should be computationally easy to do. Doesn't mean they're hard to break the codes, but they should be easy to do. And then there are some other properties we would like, because the whole point is to keep everything secret from Eve. We don't want the enemy to intercept and read the message we are sending. The whole point is we want to have secure, secret transmission of our information. So there's an additional property we'd like, which is, suppose for a fixed key K, we have some ciphertext C1, C2 up to C sub n in C. So our first image is Alice and Bob. Bob encrypts a message and sends it to Alice. We assume, right? Bob sends to Alice some encrypted message C. We assume Eve is able to intercept and read that message, right? Like maybe its message is being transmitted, by radio. So anyone can tune into the channel and get the message. So Eve can know what the ciphertext is. Her problem is to decrypt it, so she can get this one message. Suppose, in fact, she can get a large number of messages. So it might be that if you have not just one message that has been encrypted, but several, it makes it easier for you to figure out the key and decipher the text. So we would like that not to be the case. We would like our cipher, that is our encryption scheme, to have the property that even if Eve has access to a large number of ciphertexts, so Eve has a large number of ciphertexts, it is still difficult. By difficult, we mean it should be basically impossible to decrypt messages. So if you are using the same key to send message after message after message to Alice, even if Eve intercepts all of these messages, so she has a large library of encrypted messages, that should not make it possible for her somehow to figure out what the encryption scheme is. For example, suppose you were using a simple substitution cipher where every letter is replaced by a letter, 11 steps away in the alphabet. We know what letters occur most frequently in a language. So if you have a large number of texts, you can look and see in all those texts what letter occurs the most often. Guess that is, in fact, let's say the letter E, which might be the most frequently occurring letter. If you know that a certain letter corresponds to E, then you know how many steps around the alphabet circle you had to go to get from E to that letter. And once you know the number of steps, that's the key. Just from that, you can break every message. So this simple substitution cipher on the alphabet fails to have this property. If you have a large number of ciphertexts, it should be easy to decrypt the message, not difficult. So that's not a very good cipher. So we would like a cipher to have this property. Another property is the following. Suppose the enemy, Eve, obtains a whole collection of messages and how they've been encrypted. So you have message one, plain text, and ciphertext. So this message, when it's encoded, it gives you this ciphertext. And you have another message, M2, another plain text, which encoded gives you the ciphertext C2, and so forth. And suppose you have N, so we have N pairs. So the enemy knows what the message was that was encrypted and gave you this ciphertext for some large number of messages. It should still be difficult to decrypt messages. So knowing a large number of plain text ciphertext pairs in itself should not allow you to figure out how you got the ciphertext from the plain text. And we could even refine this a little bit. Suppose the enemy, Eve, picks N plain text, M1, M2, up to M, somehow gets them encoded and obtains the corresponding pairs, the plain text and the ciphertext, the plain text and the ciphertext, and so forth, the plain text and the ciphertext. It should still be difficult to decrypt the message, right? So these are some properties of an encryption scheme that we would like a symmetric scheme to have. Again, symmetric scheme means Alice and Bob have the same information. Essentially, what that means is the key that you use to encode your message should also be the key that you use to decode the message. That's the symmetry of this. Now, a message, which is plain text, might be something as simple as attack the bridge at 5 a.m. or buy 10,000 shares of IBM, right? So these are plain text messages. But what one does is, before you send a message, it's easier, it's better, it's standard to convert your messages to numbers. So for example, each letter corresponds to some number. So you take each letter, you write it as the corresponding number, and you get some long string of digits, right? So you convert your plain text to a number. And usually that's done in binary. So, for example, and this is the most common thing, we choose, we want not just a number, but a number written in binary, which means a sequence of zeros and ones. So you fix a certain length. So typically it might be 8. So consider binary sequences of length 8. So you can think of this as 8 boxes, and in each box I put a 0 or a 1. Right? So I have, this is going to be a bit string, a sequence of zeros and ones of length 8. Right? Now, how many bit strings are there? So the number of bit strings of length 8, which is called a byte, spelled with a Y. The number of bytes, you have 2 choices for each number. It's 2 to the 8th, or 256. So typically, and early on certainly it was the case, you assign to every letter and every number some bit string or some byte of length 8. And you had 256 choices. So you could represent lowercase letters, uppercase letters, the digits from 0 to 9, punctuation, other things that you might want as a bit string of length 8. And so every one of these letters, and like a space, for example, would also correspond to a certain bit string. So every one of these letters would give you some sequence of digits of length 8, and you run this together and you get some very, very long binary number. And the process by which you can convert a string of words into a number, everybody knows. There's no secret about that. You convert your message to some plain text, which is a long binary number. And everyone knows Alice, Bob, and Eve how to go back and forth between words and numbers. All right, there's no secret about that. So what you're going to be communicating from Bob to Alice is some number in binary. All right. And which is some number. So all of cryptography now comes down to having a big number, which you transmit. You encrypt the number. So you convert your number to another number. That's the ciphertext. And that's what you transmit from Bob to Alice. Right? This number. And Eve intercepts and reads that number. She just has to figure out how you get from the number back to the original number, which is the plain text. So cryptography has become this arithmetical problem of, given a number, how do you encrypt it, change it to another number in a way which Alice, who gets the number, knows how to get back, to decipher, to decrypt, to get back the original number. But Eve, when she intercepts the number, has no idea what to do with it. That's the whole problem. Any questions about this? So in a symmetric cipher, Bob has a key that he used to encrypt. Alice has a key that she uses to encrypt. They both have the same key. Eve doesn't have it, and hopefully she can't figure out what to do. Okay. So let me give an example of a simple encoding scheme. So here is an example of a symmetric cipher. So remember, everything is a number. Everything is a number. Let P be a large prime number. Let's say P is like 2 to the power 160, which is a common initial choice. That's a big number, right? That's like 50 digits long, maybe. That's a big number. So let P be a large prime number. And let's say the set of keys and the set of messages and the set of ciphertext, so the keys, the plain text, and the ciphertext, it's the same set. It's all the numbers between 1 and P minus 1. And then I could think of these as integers, but actually what I want to do is take these to be the non-zero elements of the finite field with P elements. That is, you look at the congruence class as mod P and throw away the zero class. This is all the non-zero congruence class as mod P. And P is so big that, let's say that our ciphertext as an integer is some number in there. Okay. So what Alice and Bob randomly select and share a key, K, which is some number in this set. So Alice and Bob know the key K, and no one else does. Right? So our encryption system is going to be what? So if you have a message M that you want to encrypt using the key K, let's say it's this. It's going to be take M and multiply it by K mod P. All right? So that's the ciphertext. Right? You take M. M is a number between 1 and P minus 1. K is a number between 1 and P minus 1. Multiply K times M and reduce it mod P, so you get another number in this set. So what Bob sends to Alice, the plain text is M. He's sending the number K times M. Right? That's the encryption scheme, K times M. What is the decryption scheme? dk of M. Well, when we were studying congruences yesterday, we proved the following theorem. If K and P are relatively prime, then there is a unique number K prime such that K prime is also relatively prime to P, and K prime times K is equal to 1 or congruent to 1 mod P. And given K, it is easy to compute K prime. So Alice and Bob pick this number K. They can then easily compute K prime, which is the multiplicative inverse of K mod P. And our decryption scheme is d sub k of C. How do you decrypt C? It's going to be k prime times C mod P. So you have to think about this for a minute. What is going on? Bob starts with M. He multiplies M by K and reduces it mod P. And that's what C is equal to. Alice receives C. What does she do with C? She takes C and multiplies it by K prime C and reduces that mod P. Why does this work? Well, because K prime C, what is C? C is K times M. So that's K times M mod P, which is K prime times K times M mod P. But K prime K is 1. So this is just M mod P. So when Alex receives the ciphertext C and multiplying by K prime, she gets back M. Right. Now, that's the encryption and decryption algorithm. What about Eve? So from Bob to Alice, what's transmitted is C. And Eve intercepts and gets C. But from C, how do you get M? How do you get back from the ciphertext to the plain text? Well, you have to know K. Because if you know K, you know K prime, and you can multiply C by K prime and you're done. But Eve does not know K. Eve does not know K. What can she do? She can guess. Well, K is a number between 1 and P minus 1. P is about 2 to the 160th power. You're not going to make a lucky guess out of a set of 2 to the 160 elements to find K. Right? I mean, you might, it's not even 1 in a million, it's 1 in something much smaller than a million. Or 1 in something bigger than a million, much more unlikely. So long as the key is secret, there's nothing that Eve can do. Right? So in this encryption scheme, and it's symmetric. Symmetric, again, means Alice and Bob have the same information, the same key, right? So this is a symmetric cipher. Both Alice and Bob share the same key, right? That's the symmetry in this, right? Now, you might say, how does it happen that Alice and Bob have the same key? Somehow, to start this process, the key had to be sent to Alice and to Bob, or Bob had to send the key to Alice. How do they have the same key? Right? You have your secret agent in occupied territory, and he's monitoring enemy troop movements and has to send it back to you, and everything has to be encrypted, because if the enemy figures out what's going on, they can find the spy and kill him. So, and the keys have to change actually frequently, because if you use the same key too much, it makes it eventually easier to decipher these messages. So Alice and Bob have to share the same key. And the question one can ask is it possible for Bob and Alice, here's Bob, here's Alice, here's the world, and they're far apart, right? Is it possible for Bob and Alice somehow to end up with, to get the same key without one transmitting the key to the other? So you have to think about that for a little bit. That's really an interesting question. Like, you're Bob, you're Alice, you're far apart. You need to be able to send messages to each other, encrypted easily, decrypted easily using a key. Each person needs to have the key, but you don't have a secure communication channel set up yet. Eve can intercept any message you send. So if Bob sends the key to Alice or Alice sends the key to Bob, Eve will intercept the message and she'll know the key, and your code will no longer be secure, right? So this is what you might consider to be a kind of an asymmetric problem, because when you start off, Bob and Alice don't have the same key. They don't have the same information. So what can they do? So for a long time, this was a kind of unsolved problem in cryptography. And it wasn't just unsolved. People thought it was impossible to solve, that there wasn't any way for Bob and Alice to somehow end up with the same key without one of them sending the key to the other. Right? And then, in an absolutely brilliant piece of work, two investigators, one was named Diffie and the other was named Hellman, came up with an asymmetric cipher to enable Alice and Bob to have the same keys without one transmitting it to the other. So there was some asymmetry. In this, Bob knows something that Alice doesn't. Alice knows something that Bob doesn't. They can't communicate to each other what that secret knowledge is that each of them possesses, but somehow they'll be able to figure out a key. Okay. This also historically indicates something that makes it very difficult to write a history of cryptography, because Diffie and Hellman came up with a scheme and eventually it was declassified and published. They were Americans. It turns out that in the British spy world, someone had actually come up earlier with exactly the same scheme, and it was considered so valuable, they didn't share it with anyone, including the Americans. But from what we know now, this Diffie-Hellman scheme was discovered earlier by people who worked for the British equivalent of the National Security Agency. The National Security Agency, NSA, is an agency of the Defense Department responsible for cryptographic matters, coming up with secure codes for the US to break and figuring out ways to break everybody else's codes. So there's the British equivalent And there are people working there who actually came up with this scheme before Diffie and Hellman. But again, we don't even know if they're the first. It might be that someone in Polish intelligence or Russian intelligence or Brazilian intelligence or Nigerian intelligence, somewhere in the world, other people came up with this idea, but everything was classified secret, so no one knows. So this is now universally called the Diffie-Hellman scheme, because they certainly came up with the idea independently. It just is that historically they may not have been the first, and one may never know who in fact was the first. So I want to describe this because this is in fact one of the key ideas in cryptography, this key exchange through some asymmetrical knowledge. So again, here is the problem. Alice and Bob must end up with the same key. That means the same method to encrypt and decrypt messages. So they have to be able to share a number somehow without transmitting the number. And for this, we use a little bit of elementary number theory. I want to make sure I use the same notation as the text. Okay. So the underlying mathematics is what we can call the discrete logarithm in number theory. So let's just recall what a logarithm is. So if we want to know, like in calculus, the log of a number x is the number y such that e to the y equals x. Right? So given a number x, you want to know what power of e is equal to x. That's in calculus. Let's go to number theory. Suppose we have a prime p. So, and then we have the field fp, which is the numbers 1, 2, 3, up to p minus 1, with addition and multiplication defined modulo p. And fp star is fp when you delete the number 0. So it's just the numbers 1, 2, 3, up to p minus 1. And the big theorem that we stated but didn't prove, because it takes just a little bit too much work for us in cryptography, says that there exists a number g such that the set of numbers from 1 to p minus 1 is exactly the powers of g. G to the 0, which is 1, g, g squared, g cubed. These are all distinct, g to the p minus 2. These p minus 1 non-negative powers of g give every residue class, every congruence class from 1 to p minus 1. And g is called a primitive root. So For every integer or congruence class X in 1 up to p minus 1, there is a number y between 1 and p minus 1, such that X is g to the power y. So this is just like in calculus, the log of X, it's the y such that e to the y equals X. In number theory, if you fix a prime p in a primitive root g, the logarithm of X with respect to this base g is equal to y, means y is the power of g. You raise g to the power y to get X. And this function is called the discrete logarithm. Right? So, or to just change the notation slightly, the log of a number h to the base g is equal to X if g to the X is congruent to h mod p. That's the definition of the discrete logarithm. Now, what's an easy problem? Given X, compute g to the X. What's a hard problem? Given h, compute the log of h to the base g. That is, to compute a number x such that g to the x is equal to h. And this is very, very, very hard. Right? And it's actually quite interesting because if I suppose my plain text were X, and I want to transmit this. So I take X, I compute g to the X equal to h, and I transmit h. So Eve intercepts h. She knows what h is. She has to find the x such that g to the x is congruent to h mod p. That is, she has to compute the discrete logarithm. That all by itself is a very, very, very hard problem. Okay. So we should keep that in mind as background when I describe what is called Diffie-Hellman key exchange. So again, here's the problem. You have Bob, far away is Alice. They need to be able to communicate back and forth in such a way that Eve, who's sitting here intercepting the messages, she intercepts the ciphertext. If she knew the key, she could decipher the message. Right? But Bob and Alice, at the beginning, they don't have this key that they share. So they need to somehow find a way to communicate a key that they both share, and Eve will have no idea what the key is. Okay. So this is what I'm about to do is very important because this is really the first serious encryption scheme that we're going to describe in this course. So you have to really pay a lot of attention to what information Bob and Alice share. And Eve, you have to understand, Eve knows everything that goes back and forth between Bob and Alice. So first, somebody, Bob, Alice, whoever, first choose a large prime number P. Okay. Second, choose a non-negative integer G, which we reduce mod P. That is, we only need to look at numbers between 1 and P minus 1. Okay. So the prime P and this number G, Alice and Bob share, and Eve intercepts it, and Eve also knows those two numbers too. Okay. Okay, but now comes the tricky part. Alice, so these two numbers are shared, the prime P and the integer G. Alice chooses a number A, mod P, that she keeps secret, which means does not tell Bob. So Alice has picked some number A that's secret. Bob doesn't know it. She doesn't tell anyone. She doesn't transmit it. Bob chooses a number B that he keeps secret, does not tell Alice. So Bob all by himself picks a number B. Alice by herself all picks a number A. They don't tell anyone. Okay. But then this is what Alice does. Alice computes the number A, which is G to the power A mod P. So Alice takes her number A, which only she knows, takes the number G, raises G to the power A mod P, and reduces that mod P to get this number A. And Bob takes his secret number B, little b, and he computes some number capital B, which is G to the power B mod P. So Alice knows little a and no one else does. Bob knows little b and no one else does. Alice computes capital A and Bob computes capital B. And Alice sends her number capital A to Bob, and Bob sends his number capital B to Alice, and Eve, sitting there, intercepts both of those numbers. So Eve knows A, but not little a. What is little a? It's the logarithm, the discrete logarithm of A to the base G. But I said computing a discrete logarithm is hard. So even though Eve knows capital A, she doesn't know little a. And Eve also knows capital B, but she does not know little b, which is the logarithm of capital B to the base G, because computing these discrete logarithms is too hard. No one can do it. Okay. Again, now Bob knows capital A, but Bob also does not know little a. He just knows capital A. Alice knows capital B, but she also does not know little b. So they have asymmetric knowledge. They don't know the same thing. But here's what happens next. So this is the magic of all this. Alice knows capital B. Alice does the following. Alice computes B to the power A mod P, right? So computing powers of a number mod a prime, we already saw how to do that in a very computationally effective way. So Alice takes this number, capital B, that she got from Bob, she raises it to A, and then reduces that mod P, and she gets a number, we'll call it A prime. So Alice has the number A prime. What can Bob do? Bob can do the analogous thing. Bob can take the number A that he got from Alice, and he raises it to his secret number B and reduces that mod P, and we call that capital B prime. Right. So now Alice has the number A prime, Bob has the number B prime. But the miracle is that A prime, which is congruent to B to the A, mod P, every calculation is mod P, B to the A. But B, what is B? B is G to the little b. So that's G to the little b raised to the power A mod P, which is G to the AB mod P. And B prime, which is congruent to A to the B. But what is A? Capital A is G to the A. So that's G to the A to the B, which is also G to the AB mod P. So A prime equals B prime. So somehow now Alice and Bob, in some miraculous way, end up with the same number, which is going to be the key they use for encryption and decryption. So they have somehow shared the key in such a way that no one can, intercepting all their messages back and forth, know what the key is. That is, Alice and Bob have exchanged the key securely, asymmetrically, and now they're in business to do whatever cryptography they want to do. So let me do a numerical example. I'll pick an example in the book. So the example uses numbers that are small enough to compute with your home computer, but too big, but way too small to be used in real life. In real life, again, we pick a prime, which is like 2 to the 180 or bigger. It's huge. So this is example of Diffie-Hellman key exchange. So the idea is for Alice and Bob to somehow come up with the same key that can be used in cryptography before they have any cryptographic method at all. So let's suppose we take, so Alice and Bob choose the prime number P equal to 941. And the primitive root G equal to 627. Now, if you want to check that 627 is a primitive root, you have to run your computer a bit. You have to write a little program to show that the powers of G up to 600, up to 940 are distinct. So every number, every non-zero number, or every number from 1 to 940 is congruent mod 941 to some power of G. But we take this as given a primitive root. So Alice has the secret number. This is really secret. She doesn't tell anyone. He chooses A to be 347 and computes the number capital A, which is G to the A mod P, which is 627 to the power 347 mod 941. And when you do this calculation, you get 390. How do I know that? I didn't just do the calculation, but the authors of the book did, and this is the number that you get. Okay. So this is the number capital A. And this is the number Alice sends to Bob. So I have Bob, Alice, and Alice sends to Bob the number of 390. So Bob picks his secret number, B equal to 781. And he computes his number capital B, which is G to the B mod P, which is G 627 to the power 781, which turns out to be 691 mod 941. And Bob sends to Alice the number 691. So Alice sees the number, sorry, Eve sees both of these numbers, 390 and 691. But what's she going to do? See, because the key, what is the key going to be? The transmitted key, I will put transmitted in quotation marks because the key itself was never transmitted, just these numbers. The key, well, Alice takes Bob's number, 691, and raises it to her secret number A. So this is capital B to the A. B is 691, and the A that Alice picked was 347. And if you take 691 to the 347, but what was 691? 691 was 628 to the 781 times 347. And somehow, if you do this calculation, you get 470 mod 941. And Bob takes the number capital A that Alice sent him and raises it to his secret number B. Capital A was 390, raised to the number little b. Bob's secret number little b is 781. And so this is 390, but what's 390? 390 is 627 raised to the power 347, and that's raised to the power 781. It's the same number, of course, and this is 470 mod 941. So Alice and Bob somehow both come up with the number 470, which is the key that they share. So they now share this key, and this key can be used for encryption and decryption by any symmetric cipher. And Eve is helpless. Eve can't figure out these numbers. The reason Eve can't figure out this number, or what would enable Eve to figure out this number, is so Eve intercepts the number A, which is G to the B, and B, which is G to the little a, and Eve knows the prime P and the primitive root G, but from a knowledge of G to the A and G to the B, Eve cannot compute A or B. And she needs A or B to get K, because the key K is G to the AB. So if you know B and you have G to the A, you can get G to the AB. If you know B and you know A, you can get G to the AB. But knowing G to the A and G to the B, as far as we know, it's too difficult from those two bits of data to figure out what A and B are. You'd have to find the discrete logarithm or one or the other, but even knowing both of these, there's no way to find the discrete logarithm of either one. This is sometimes called the Diffie-Hellman problem. It's a very hard computational problem in number theory, and it is, again, maybe someone in the secret world knows how to solve this problem. But in the non-secret world, this is still a mystery. Okay. So what I've just discussed is a little bit of the general nonsense theory of cryptography that you find at the end of chapter 1, and most of the first couple of sections of chapter 2, where we introduced the discrete logarithm problem in number theory. Given a prime and a primitive root, you define a logarithm. How do you compute it? Very hard. And this Diffie-Hellman key exchange system. So this is really, really, really important. And I would encourage you over the weekend to spend a lot of time studying this. And when we resume on Monday, we'll begin to talk about another cryptographic scheme, which is called the El Gamal public key crypto system. And it's very closely connected to Diffie-Hellman and related to the discrete logarithm problem. So that is the main subject of what we're going to do at the beginning of next week. So we're really starting now cryptography. We're learning secret codes. And the problems tend to be hard because you have to do some computation, and you need to put some time into it. If there are any questions about what we're doing or questions about any of the homework problems, I have another sort of problem session office hour tonight at 7, and there'll be another one at certainly tomorrow afternoon, I think at 5 o'clock. And I will send an email about that. That is really all I need to do today. Any questions before we stop for the morning?
Professor, I have a question.
Yes, sir.
So when is the midterm? Is it on June 15th or the 20th?
No, it's exactly what it says in the information for the course. The
On the
midterm.
assignment, right?
What?
On the assignment syllabus?
No, in the course information, the midterm is the 15th.
Okay, because when I was looking at the
Final
assignment,
is the 29th.
yeah, because when I was looking at the assignment, it said June 20th, there will be solving midterm review sheets. That's why I said on it.
Oh, that's that's just when the homework is due. That's not the date of the midterm.
Okay,
The
got it.
midterm is Thursday, a week from today. That's
So June 15th.
exactly the middle of the term. And the final exam is the 29th, which is the final exam day for this summer semester.
Okay.
Professor,
Yeah,
how to get 470 you got? Both.
sorry, how to get what?
470, the key, asymmetric key A and B.
Oh, well, if you have a computer, you have to
Mhm.
do this calculation. 628 to the power 781 times 347. So that's some enormous integer. You divide it by 941, and the remainder is 470.
Okay, so calculator,
You
can
cannot
we
do this with pencil and paper. It's way too big. And you can't
Okay.
do it with a calculator either, because your calculator can't handle numbers this big. You need a very good computer, or you need a computer.
Which website in computer?
Sorry?
Which website in the computer I will do?
I have no idea I mean, there's no website. If you
Maple?
know Maple, for example, you could try it in Maple.
Okay.
But it's not, there's a website. There might be a calculator that's part of your computer program. You could try and use that. But it has to be, your computer has to be able to handle numbers that are this big.
Okay.
Okay.
Thank you.
Other questions, perhaps? All right, well, if you go outside, be careful, don't breathe the air too much. Next lecture will be 11 o'clock Monday morning. Have a good weekend, all.
Thank you.
Thank you.
Bye.